So this is where we left off. We have dichromate, very, very powerful oxidizing agent. It is chromium 6, going down to chromium 3. Therefore, it's going to oxidize everything around it while it gets reduced. It can't go any higher, so it has only one pathway. Lots of protons. We're going to ignore that for now. We're going to ignore the fact that this is being performed in acid, because if we think about it at any level at all, that's going to be a problem. So far, everything that we've done has been in terms of concentration, and we've said that activities are real and the concentrations aren't. That's going to be a problem for us later on. That itself is going to mean that we have to switch to activities, but we'll just go with concentrations. All right, so here's my overall reaction. This thing is getting reduced, and that thing is getting oxidized. I'm not sure we wrote those on the board the last time.
I know last time. I just kind of give up. I just started listening.
Okay. So the first thing that we have to do, this is our overall reaction. We have to break those into half reactions. So there's a little skill to this. Obviously, the chromium that is here belongs to the dichromate that is there, okay? And I think that also, obviously, the iodide that is here is tied to the iodine that is there. Okay. This top one. Oxidation or reduction? It's a reduction, so which side do the electrons go?
On the left.
And how many electrons are we looking for?
In that specific reaction, it'll be 3, but we might have to change because it's going from 6 to 3. But there's
Two of them.
overall, so it's 6.
So this dichromate is a chromium 6. So this is 2 3-electron reductions. So I need 6 electrons here. This one right there.
There'll be 6 electrons on the right.
We go from iodide to iodine, where this is a -1 and that's a 0. So that's 6 of them. And reductions. So I'm going from +6 to +3, lowering my oxidation state, so that one's a reduction. This one is written as an oxidation. Okay, we're almost there. We cannot leave it just as it is, because in half reactions we don't really need to balance, but I've accounted for all of these atoms, ions becoming atoms, this molecule, and I've accounted for all of them. What's going on with the oxygens? Well,
They're going to water.
well,
They end up going to water.
yeah. So this one, we need to account for the oxygens by turning them into water.
Can't you just
Okay.
pretend that, like,
Yeah.
could you drop the oxygens? And say CR.
Yeah, sort of.
To the 6+.
sort of, because our focus is definitely here. But it's kind of dangerous to do that because these big high-powered oxidizing agents, the chromates, the dichromates, the permanganates, they do different things in the presence of acid than they do in base. Permanganate in acid will go all the way down to manganese 2, but manganese in base will stop at manganese 4. So the two things, there's a different outcome, and it's not the way that it's written in the appendix. The appendix is going to include the missing components. Missing components. What's missing? Still something missing. Because we've accounted for the oxygens now, but in counting for the oxygens, the 7 waters, we're missing these 14 acidic protons. So I'm going to squeeze them in here because they are not the important thing. Okay, that's a reduction. This is an oxidation. We were told 2 whole weeks ago that this reaction is spontaneous. Okay. When we go and we look in the appendix, I think it's Appendix H in this book. Let's go do it. Because I don't think I need. All right, Appendix H. Multiple pages. They are listed alphabetically by important elements. So all your chromiums are going to be listed together, and all your iodines are going to be listed together, and chromium, lower in the alphabet than iodine, will be listed first. I'm going to want the standard reduction potential for the acid reduction of dichromate.
1.36.
You have that as a 6. I have that down as a 3.
Just in reverse, you make it.
Yeah, because it's being oxidized. 0.535.
Will it be a negative?
No, well, he's asking for the reduction.
Tell me what it says in the book.
0.535.
Okay. What it says in the book, it doesn't have a plus. 0.5. I'm going to round this up. No, I can keep the 3.5 because I have 3 significant figures in both of those numbers now. That's the number. Does that number match this? Did you pull that from the appendix? No.
We pulled it.
What
flipped and
you pulled from the appendix was I2 plus 2E makes 2I minus.
Yes.
Okay. What if I multiply this by 3?
Nothing happens.
Yeah.
Because
you-
of a word.
These are intensive. Yeah, if I multiply that by 3, nothing happens. This is the reduction potential for this reaction, which is also the reduction potential for that reaction. The oxidation potential would be the negative value of it. Okay. Cell potential is one of the potentials minus the other potential. Do you remember which way around it goes?
Reduction and the reduction and the oxidation.
We want the standard reduction potential of the which one?
The reduce.
Okay, and where does the reduction happen? Which of the two electrodes?
The cation, or
Cathode. So this is the actual reduction. And then we're going to subtract from that the reduction potential that we find for the anode, where the oxidation happens. Okay? This is the same as saying it's the reduction potential of the thing being reduced plus the oxidation potential of the thing being oxidized. Okay? So to get to the oxidation potential, you would just flip this and have that be a negative number. We're going to put the negative here. Okay? Stick your numbers in. Don't care what the appendix says. We're going to be using pluses and minuses. Did you use the 3, 6?
Yes.
36.
Yeah.
Oh, significant figures.
So I have this down as a 1.33. If you want that stay consistent with what our textbook tells us,
Oh, okay.
let's go ahead and change that to be 1.36. I must have got it from somewhere else. Okay, and then that gives you a number that is what?
0.825.
Volts. We're almost there. Do need to know whether that's a plus or a minus. And only writing the minuses in is a bad habit. You should also write the pluses in. Okay. Write that down. The whole point about this was you just found the standard cell potential. I'm going to change the numbers. What if we went to non-standard concentrations. What if the concentration of our dichromate is, well, we've got three significant figures. I'm going to give you three. 2 moles per liter. And the concentration of acid is 1 mole per liter. And the concentration of iodide is 1 mole per liter. And the concentration of chromium 3 plus, I think this is where the hand goes on the scale to tilt the balance here. 10 to the negative 5. We have three significant figures now, so we can keep the three significant figures that are already in our answer. And the standard, just erased it, standard cell potential was plus 0.825 volts, correct?
Yes.
All right. Now what do we do?
What are we looking for?
What's the new voltage? What's E cell? It's no longer E standard cell, it's E cell. Go back to what we did before we did the big ugly acid catalyzed oxidation. Acid promoted oxidation. We looked at the Nernst equation. And the Nernst equation tells us what? The Nernst equation tells us that the value of a cell potential at non-standard conditions is the value of the standard cell minus 0.059. We're going to put the second one here. 1/6. Sometimes we just round that up to a 2 over n log of Q. So there's a Q. Q is like K, only at non-equilibrium conditions. It's the concentration of the products divided by the concentration of the reactants. And you have stuff on the board. Are you missing information?
Whoa! Like that every time. I don't. We're good then.
That's a solid. It has no concentration. This is a liquid. It has no concentration. These do not belong in a K expression. If they don't belong in a K expression, they don't belong in a Q expression either. So you have product and you have reactant.
Yep.
Thank you. You've got to remember your chemistry too. What do the coefficients do? Yes. Coefficients become powers. What you doing this afternoon?
After what time? I have class at 2. She always cancels though, and it ends at 3. But other than that,
I have lab at 2.
mhm,
And if Joseph has baked off the jars,
mhm.
we can go collect flowers.
Okay, good. Because I was looking at it, and the flowers had to be fresh.
Yes.
Like it said, like an hour within collecting the flower, you have to run the. And it was saying it's better to put them in vials. All the procedures.
Mm-hmm.
So can we collect flowers today?
Yeah.
We can. Okay. What time?
I have between when we finish and 2,
Okay.
or after that, probably about 3.
Okay. I can't do 3, so I can do in between.
Yeah. You run the risk that the flowers will rot,
Mm-hmm.
and what you're smelling is rot, not flowers. But also, we run the risk of, if we only give them an hour to saturate the spini, that we don't get anything. So we'll collect them, and then we'll run them over. We'll collect, we'll absorb
So you wanna
overnight,
put them-
and we'll run data tomorrow. We can always close the spinis.
Okay. Do you want to put them in those jars though?
Yes.
Even though they're so little, can we put multiple? Cause some,
Yes.
okay, some procedures said like 50.
I think we need about 5 grams.
Okay.
I don't know how much. I don't know how many flower heads 5 grams is, but probably quite a few, quite a lot. Sorry? So we need some scissors and some jars. We'll go do that.
We'll be fine. Are we gonna do it overnight?
I think so. So then we'll run some experiments tomorrow.
Okay. Good.
We'll run some collections tomorrow.
What time tomorrow?
I only have 2 things on my calendar for tomorrow. I have a class at 11 and I have a meeting at 3.
Could it be in the morning?
It could.
Okay, thank you. Because I work in the max.
Depends when Joseph's available.
Okay.
I got 5 times 10 to the negative 11.
Oh, you gave me a number. 5 times 10 to the negative what?
11?
Yeah.
Great.
All right. So our product, the only product that we have is chromium 3 plus, and there's 2 of those. So that value is going to get squared. And then our reactants are dichromate and H plus raised to the power of 14. It's a good thing, there's only one of them.
Yeah.
And then iodide raised to the power of 6. I know, this is kind of a cop-out when these end up being 1s, because 1 to the 14, you could have given me, come on. The people that generated this question could have given us something useful. So 1 times 10 to the negative 5 squared over 2. 1 to the 14 is 1. And 1 to the 6 is also 1. All right. So this is basically 1 times 10 to the negative 5 times 1 times 10 to the negative 5, which gives me 1 times 10 to the negative 10, right? And then divide it in half, which gives me 5 times 10 to negative 11. You do it in the head. All right. Go find the value of E. E, cell, is the standard value minus this. Where did that come from?
Where did it come from?
Great question, Dr. McGuire.
I forgot.
It's in your notes.
Don't know where I put it.
I
I can't find it.
I can't even find the Nernst
I know. Did we have?
Did we?
I feel like we've talked a lot about it,
But I don't
and then I never wrote it down.
Ever.
Me too.
Ever.
I would have written it down.
Me too.
I don't think I've seen it before.
Me neither. Hold up. Dr. McGuire.
I don't think we've
McGuire.
actually-
I feel like you're
Sure, we
gaslighting.
did the Nernst
I
equation.
thought we did.
I feel like he's gaslighting.
I feel like he's gaslighting me too, but I can't find it in my notes. I only had a couple pages in. Talk about current.
We did a Q, right? Or did we not already do one of those?
Dr. McGuire.
Okay. Well, maybe we didn't
We're
get to
fine.
it.
Okay, you make me feel bad because it's like,
I don't know.
Okay, that is from here. That's a simplification because the long form
Long.
is
Oh, wait, it's not a big turn.
E. No. Standard minus R T over N F
wait.
log of Q. And because this is standard, at 25 degrees Celsius, 298 Kelvin, R and T and F
Yep.
all condense down
Yes.
to that number.
So N is moles of.
And N is
That's the oxidation thing.
it's
Oh,
got
is
to do
it
with
number of
oxidation,
electrons?
number of electrons
Ew,
transferred.
Yeah. I feel like we should get a different letter for that,
We really should.
but I'm not gonna complain.
It's okay.
I don't make the rules. Okay, so 6.
So I have that right here before what we do here. So we must have done it.
We might.
I say we must have.
Well, I
Maybe we
remember
skipped
last
it.
time we stopped on a, didn't we stop on like a cliffhanger? He was like, do this at home or blah blah blah.
Yeah.
blah.
Yeah.
To break that into half reactions.
Oh, so you're saying before this you had us doing that?
It
Swear it's
looks
not.
like it.
Unless I
I swear
did
it's
not
not.
take a singular note last
It looks like it. Well, it's on the board now.
Oh, well, we learned it now.
We learned it now.
We got it. Okay. Great.
I like taking notes, so.
I know. I would have written that down.
So you use the Nernst equation for non-standard conditions because it has a Q in it. So our E cell is our standard number, which was plus 0.825 volts minus 0.05916, all divided by n to the log of 5 times 10 to the negative 11. Feels like I said 12 out loud a few minutes ago. I guess it was 11. What's the n?
6.
Oh.
Yeah.
We have 6 electrons. It's a 6 electron redox reaction. Okay.
So Dr. McGuire, Joseph said you'll be here tomorrow and what other day?
Today. He might be here Thursday as well, don't know.
Okay.
He seemed quite helpful.
Quite helpful. Okay.
I contacted him yesterday. He said, oh, I'll be in. Came in and he spoke to me. Shall I clean the speeds? Shall I break off the jars?
Oh.
He's been very helpful.
He is helpful.
Yeah.
What does that do to our number?
That's the second word I got down. I thought it.
Yeah, it'll decrease your standard. So,
Will it though? Will it? Okay.
Because that's.
Is this number larger or smaller than 1?
really smaller than 1.
Yeah. So when you take a log of a number that is less than 1, the log is negative.
Yeah.
And then we're going to subtract
That's.
that negative.
Okay.
So when your calculator gives you an answer,
Uh-huh.
look at what you've got and say, don't just believe that your calculator has done it right. Does it make sense? That's a very small number. The log of that small number will be a negative value. You're going to subtract a negative value from a positive value. Sometimes this will be a negative number. Sometimes it'll be a positive number. Make sure it makes sense. So I have a positive number and I'm subtracting a negative number from it.
So 0.926.
Oh yeah, okay, so the number I've got written down is a little bit different than that because I used a different reduction potential. Yeah, 9.2 volts,
Positive.
like it. There you go.
So all that we just did was finding for non-standard conditions.
You just found the cell potential at non-standard conditions.
So-
Anyone can find the cell potential at standard conditions because you just read the numbers from the appendix.
Okay, that makes sense.
And you can do this question backwards that says, oh, you know, that reaction gives me a cell potential of 0.825 volts, but I really want 1 volt. Can I move Q enough to give me a volt? Maybe. Maybe not. I mean, that's pretty small. Yeah, but it's like what you would do with Henderson-Hasselbalch equation and buffers of, I've got an acid in the stock room, here's its pKa, I want the pH to be a little bit different than that. So I've got a reaction, and I know what I have a voltage need. I need a voltage to be at 1.15. What can I go pick that will get me a voltage close to that? And then what can I do to the concentrations to make the voltage be the number that I want? All right. Next. We did one of these in lab.
Oh, we tried one of these in lab.
Before the break. Concentration cell. Did you look at your numbers? Did they make sense? Because it felt like you got numbers and you packed up your book and you ran.
That's exactly
Yes,
what I did.
I have that one.
I mean, I tried. And ran.
In a concentration cell, our half reactions are the same, but the concentrations are different. Electrons flow from one solution to the other. Do we remember which way? I just said that out loud, didn't I? I can't remember. In a concentration cell, the half reactions are the same, but the concentrations are different. And then it's kind of like Le Chatelier of going to try and make both sides of the cell equilibrate. So electrons flow from the dilute solution to the concentrated solution. I think we might have done this in lab. I'm not sure it's been on the board yet. Here's a nickel electrode. You can tell it's an electrode because it's a solid. And then there's a boundary. And that nickel electrode is in nickel solution.
And because it's a transition metal, it has the 2+ available to it.
It's a D8 transition metal, which means its 2+ is far and away the most stable. Okay, so that's the nickel electrode in a nickel solution. 2 lines represents the salt bridge. And then on the other side, I have the nickel again.
What do we call these?
It's in the, I think they might be called boundary diagrams or line diagrams, something like that. Not sure what the actual name is. But they're useful. So you can write any cell this way. Electrode, solution, solution, electrode.
Is it usually the cathode first?
I bet you there is a convention that says if you know, then yeah, it would make sense to write the cathode first, because that's the way that we would pull that information out into an equation, right? Into a calculation. So I'm not sure that there's really is a convention, but if there is one, it would likely be that way. Okay, where are we? Let me find the
part of the book where they say to do this? Let's see if they give a name to it. I'm not sure that I ever learned a name for it. No, I can't find it. Alright, never mind. It's in there somewhere.
Big books.
Okay. The reduction potential that represents nickel. Oh, no, no. That's an oxidation. Let's go ahead and look that up. Because I've got it written down wrong in my notes. Find me the reduction potential for nickel 2 plus. We call that, it's not, I haven't noticed it in the book yet, a couple. When you go from one ion to another ion, from one oxidation state to another, they call that a couple.
-0.236.
Okay. And how is that written?
With nickel 2 plus 2 electrons make a nickel solid.
Okay. That's a 2 electron reduction, and the reduction potential is
0.2, -0.236, sorry.
slightly different than the number I've got in my notes. Okay, here's a question. What's the value of the cell potential under standard conditions?
My gut says 0.
Under standard conditions, 298 Kelvin, 1 atmosphere of pressure, 1 molar solution here, 1 molar solution there. They're going to cancel each other out. When it's standard, there's no voltage being, there's no current, there's no voltage, there's no potential difference. Can't have a current without a potential difference. So there's no electrons changing hands here. Because there's no impetus. So what I need to do is go non-standard. When I go non-standard, I can change the concentrations here. So I'm going to make one of them be one concentration and the other be another. Okay, so I'm going to make one be 1 molar. I'm going to keep one of them under standard conditions. And I'm going to dilute the other one by a factor of 1,000. Okay. Before we go charging into this, we have to think about what information is already on the board, because that's going to tell us how to set this up. That's the direction of the electron flow. Where's the oxidation happening?
At the nickel, the diluted one.
Yes. Yes. Because we have a directionality to this flow, the dilute solution becomes oxidized. The electrons are flowing away from oxidation is the loss of electrons. Electrons flow away from the dilute. This is the dilute. And it gets oxidized. And oxidation occurs at the anode. This is my anode, and therefore the other one's the cathode. How am I going to find the cell potential?
Do products or reactors, but you know that, so since the bottom one's oxidized, the bottom concentrate, oh gosh, I'm trying to do it in my head, but they're both gonna end up on either side of the reaction. So one of them is gonna be a reactant, one of them's gonna be a product, and you'll be able to use Q that way.
Yeah.
I think the bottom one.
We should have a convention for that, shouldn't we? Of which one goes on top.
Yeah, it's the product, but is it the dilute or the concentrate?
Would it be the concentrate since we're going from dilute to concentrate?
The electrons are flowing that way, but that doesn't mean that the equation is, I think.
The cell potential for this concentration cell is the standard cell potential, which is 0. This 0 is a reduction potential of minus 0.236 volts minus negative 0.236 plus 0.236 equals 0. Right, the cell potential is 0. And then I'm going to subtract from that 0. What?
0.5916.
Over n log of q. And there is a convention for q. Dilute over con.
That's good. Where does it come from?
Don't know. My guess is somebody wants the values to be positive.
I would want the values to also be positive.
Yeah.
That'd be great.
Because if you make dilute over concentrated, this is a value that is less than 1. The log of a number that is less than 1 would be a negative number. assuming this is always going to be 0, then we get positive numbers this way. So somebody somewhere just said, stop freelancing on this. Everybody do the same thing, and everybody come out with positive values of potential. Because that's the whole point, right? What's our value of n?
2.
One times 10 to the negative 3 divided by 1 is 1 times 10 to the negative 3, which is 0.001, which is equal to negative 3. Multiplied by that number divided by that number. And then subtract all of that negativeness from this 0.
Positive 0.887.
It would be 0.0887.
Yeah, 0.0.
Mhm.
But
Mm-hmm. Okay. Are we expecting that to be a big number? No, we shouldn't expect that to be a big number because I started with 0 and have changed it. It is, however, a way to make something out of nothing, out of absolutely nothing. You want to make a cell? You can make a cell. We've got zinc in the stockroom, we've got copper in the stockroom. That's a really good cell. That'll give me 1.1 volts. And you know we were talking about pennies being zinc, right? If you put a stack of pennies, you take pennies and you take copper sulfate solution and you just put little pieces of paper between the pennies and you stack them all up in a tower. You made a battery.
For real?
Because the zinc metal and the copper sulfate separated from each other, yeah.
We should have done that instead of counting all of them pennies.
Yeah! Dr. Mari, can we have a new project?
We could make a primitive battery that way. We could give it a shot. Yeah. Yeah. But then you go to the stockroom and you find out that, in fact, I don't have any copper, and I don't have any zinc, and I don't have anything. All I've got is nickel.
Wow.
I've got a chunk of nickel and some nitric acid, or some hydrochloric acid even. And you take your nickel and you dissolve some of it in the acid and you make the nickel chloride or the nickel nitrate, and then you put the nickel in the solution, and then you separate it from another piece of nickel in another solution. And as long as they're at different concentrations, you've just invented a potential difference. And with the potential difference, you'll get a flow of electrons, you'll get a current. You can make something out of nothing. It's really clever.
I have a question, Dr. Warrior. So I know multiple cells make a battery. A singular cell, does it do anything? Creating a potential difference, what can that do?
It, like,
It can do whatever a battery can do.
So a single cell can do whatever a battery can do. Then what's the difference?
Just more, having more of them gives you more.
Okay.
Yeah. can still generate a voltage. But, you know, having more of them gives you more power. Okay, let's see, what's our next topic? Who?
We're done with this?
Yeah, we could go collect some flowers, go pick some flowers.
Let's go, let's go. We're being serious.
Yeah. I've got a little thing called a Latimer diagram coming up next. It's going to help us find a missing numbers that are missing from the appendix. Because the appendix can't give us absolutely everything, but it will give us most of everything. This is a very good appendix, that one. But if we were to look at a lesser appendix, go, oh, this value is missing, we could figure it out by looking at the values of the other reduction potentials. All right, let's go see if Joseph has baked off some jars for us, and we'll go collect some flowers.